Hello everyone. I hope you all can see my screen and hear me. Hello Siddharth, hello Rupsa, Samson, Warren, Lakshmi, Prem. A very good morning to all of you. Today we will start with the next topic, that is rotation of rigid bodies. Last class we solved some of the problems of conservation of momentum and collision. Next, I'm going to give you some more video links on problems on the same topic of my own video. So you can refer to the more problem solving from there. Since we have exam, I will do it after your exam because this chapter is not for the coming exam. Good morning, Janvi, Aishwarya. So if you can hear me clearly, you can let me know and we can go ahead with the next topic in line, that is rotation of rigid bodies. And particularly in this, we are going to talk about kinematics of rigid body, or how does a body which is rigid rotate. That is the question we are going to answer. Thank you, Kunal. My first question to all of you is, what is a rigid body? Then we can discuss those things in post lecture discussion. Please be there. So what is a rigid body? Can anyone tell me quickly, shortly? Any body that does not get deformed easily with pressure, body with constant dimensions. Okay. Yes, that is the correct definition. We have a more mathematical definition of a rigid body. Suppose if these are my coordinates and if this is a rigid body, let us say, if I take any 2 points between any 2 points in the rigid body, and if I draw a vector, from say point, this is point P, this is point P, and that is point Q, and if I draw a vector from point P to Q, vector PQ, then in that rigid body, if vector PQ is always constant, both in magnitude and in direction, then in that case we say that the body is rigid no matter what is the situation. So even if there are external force applied, if this vector remains constant, and remember P and Q are arbitrarily chosen points, so for any 2 points, if this vector remains constant, then the body is said to be a rigid body always. So in practice, in real life, the bodies are relatively rigid. They are not ideal rigid bodies, because what happens is some bodies will not deform on application of small forces, but on large forces they would still. So as long as they don't reform, we keep them in the category of rigid bodies. So Mehak has a very descriptive definition of rigid body, that has a solid boundary and maintains its shape against external force of pressure. That's true. Okay, but remember that this definition has a limitation. Beyond a point, every body is deformed. So in that sense, there are no true rigid bodies. Okay, so here we are looking at the rotation of rigid bodies, the bodies which will not deform in the given circumstances. So the first thing that we are going to look at is something new, and that is called as angular displacement. So far we have spoken of linear displacements. Angular displacements can be shown in terms of theta. So suppose if you have a rigid body, some arbitrary shaped, and just for the reference I'm drawing axis. And let us say that this is some arbitrary shaped rigid body. It turns from this position, or I would rather an arbitrary shaped rigid body. It rotates about some point, say O. So if you take any other point here, then this will undergo an angular movement about the point O. Okay, so it will trace a path on a circle. Radius is R, and this is S, and this is your angular displacement. So we know that we define angular displacement theta as S upon R, and the unit is radian. That again you are well familiar with. Would it be a scalar quantity or a vector quantity? Scalar or vector? You can try to answer that. In the meantime, I'll tell you, if it's a more rigorous, we have learnt Another unit which is degrees. You know, most of the time you have drawn angles with the unit called degrees. So how degrees and radians would be related? So many ways. Remember, when it completes one rotation, we say it's 2 pi radian or 360 degrees. So 360 2 pi radians actually corresponds to 360 degrees, and therefore 1 radian would correspond to 360 degrees divided by 2 pi, which can also be written as 180 divided by pi, which can also be written as 57.3 degrees, or you can remember as approximately 57 degrees. So that's going to be a very important vector. Everybody is saying vector. Rishabh. Okay. Well, it's a very tricky situation. It's not a vector. If I would say, you will get surprised. Okay. So, angular displacement, scalar or vector? The correct answer to this question is, if it is finite angular displacement is a scalar. Do remember that. While if it is infinitesimally small, you know the meaning of these words. I suppose I'm writing the correct spelling. So I would leave this to verify. There's one problem, see problem list. In the reference book, in the same chapter, at the end, there is a problem list. One problem list, one of those problems actually explains you how to verify the finite angular displacement is a scalar, infinitesimally small angular displacement is a vector. So do find it out. Now if it's a vector, then what are the directions? So it's very straightforward. We use the right hand rule to put it in the perspective. The next topic that we will write is angular velocity. That is omega. Omega is defined as d theta by dt, or rate of change of angular displacement. So it's a derivative. software has bugs. I will have to write again. So as I said, please verify. Angular velocity, we normally defined by small omega. Small omega is d theta by dt. Okay, which is also nothing but limit of delta t tending to 0, delta theta by delta, sorry. So this is instantaneous angular velocity. There is something called as average angular velocity, which is delta theta by delta t. What will be the units? You can guess. It's radian per second. Okay. Other units we use is revolution per second. So 1 revolution per second is nothing but 2 pi radian per second. One more unit is 1 revolution per minute. You can easily guess it's 2 pi by 60 radian per second. Remember, radian per second would remain the SI unit. Directions are very straightforward. So if you have the particle as seen from front, this is the front side. So if the particle is moving this way, then the angular velocity is given by the right hand rule. So omega. So curl your right hand fingers in the direction of rotation and stretch the thumb outward. The thumb gives you the direction of omega. So remember that the direction of omega is perpendicular to the plane in which the motion is happening. Now tangential velocity is in the plane. Radius vector is in the plane. So omega is perpendicular to both. So that's a very important observation we have to remember. If it turns in the opposite direction, say if the particle moves this way, you can again turn your right hand fingers. In this case, omega will point in the downward direction. And do remember, then again it will be perpendicular to the r vector, and it will also be perpendicular to the v vector. So that remains true. Oh, that's right. So at this very interesting situation, I give you a small little problem. Those who are with pen and paper can tackle it quickly. Theta is equal to 3 t cube. Okay. Find omega. at 2 seconds. You can also find theta at 2 seconds. If radius is provided, radius is 5 centimeter for this particle, for this circular motion. Can you find out the displacement in 0 to 2 seconds? So these are the three questions that has been put. You can try to quickly answer them, not more than 3 minutes. So you can see the answers are very straightforward. Theta is 2 seconds, so you can put here. So 24. So theta would be 24 radian. How do you get omega? Omega is a derivative. Omega is 9t square, which will become 4 into 9, 36 radian per second, and S is equal to r theta, because we have just defined theta as S upon r. Therefore 5 centimeters, so 0.05 into theta in 24. That will give you your displacement. So that's nice. We can go to the next quantity that we normally come across, and that is called as angular acceleration, normally represented by alpha with a vector. So you know what is angular acceleration. It is the rate of change of angular velocity. That's right, 1.2 Rupsa. Siddharth, that's a good calculation, quick. I'm glad you people are so fast in your calculations. Remember, this course is all about practicing the application based problems. In the exam, we are not going to ask you any theory. So that doesn't mean you don't have to study theory. You have to study theory, because without studying the theory part, you will not be able to answer the concepts. So in order to answer the concepts, you need to study theory. So study theory, but test your understanding by practicing the problems. There are discussion based problems and there are numerical problems. So please attempt those numerical based and discussion problems, as many as possible. You ask me ideal figure how much you have to do, I don't have an answer. You have to do it as many as possible from the chapters which are there in the syllabus, so that you get a robust understanding of the topics and concepts which are presented. Thank you Aditya, let's going ahead. Let's talk about angular acceleration. Just like linear acceleration, angular velocity. Just like linear acceleration, which is rate of change of linear velocity, angular acceleration is rate of change of angular velocity. So average alpha is going to be, so that's very straightforward. If omega 2 is final angular velocity minus omega 1 initial angular velocity, maybe at times t2 minus time t1, I can write it as delta omega by delta t. Therefore, instantaneous angular acceleration is limit of delta t tending to 0 of delta omega by delta t. We can invoke the first principle of derivative and write this as d omega by dt. Okay. Also do remember that omega is the first derivative of displacement. So this can be written as d2 theta by dt square. We'll put a vector sign. What about directions of alpha? How do we assess? So very straightforward assessment. Remember, even in case of linear velocity, if the velocity is increasing, linear acceleration has the same direction as that of velocity. If the velocity is decreasing, listen carefully, decreasing, not reversing. If the velocity is decreasing, linear acceleration is opposite to the velocity. That same principle applies here also. So if omega increasing, alpha omega in same direction. If omega decreasing, then alpha omega in opposite direction. Just for putting on the record, if omega constant, then what is alpha? You can easily guess. Omega is constant, derivative of a constant is 0. So alpha is 0. So alpha does not exist. Alpha is equal to 0. So in problem solving and in future calculation, this becomes a very important knowledge, that you must know the idea of alpha and its direction. Units are straightforward. So units are radian per second square. Okay. So these are the three parts. Let's get to this problem once again and let us try to answer the acceleration. How much will be the linear acceleration? So theta is 3t cube. Theta is 3t cube. You will get omega as d theta by dt is 9t cube. sorry, 90 square, and alpha is another derivative, d omega by dt. So 18t. What will be the acceleration at the end of 2 seconds? So it can be put as 18 into 2, and that is 36 radian per second square. You can see that this is not a constant acceleration. It's acceleration that is increasing with time. Generally, the next concept is relation between the linear. Wait a minute. As I said, alpha is increasing with time. We can not all the situations alpha increases with time. So what happens if alpha is constant? And this is very important discussion. If alpha is constant in time, then I can write alpha as omega minus omega. I'm just changing the notation. It was omega 2 minus omega 1. I'm just writing omega, which is angular velocity after time t, minus omega 0, angular velocity at the beginning. So this is change in angular velocity divided by time. This is time at which we have this angular velocity minus time at the beginning, which is 0. So it is just writing this equation in slightly modified form. Alpha is constant. This is not going to change. Therefore, this can be written as omega 0 upon t. I can bring t this side, I can bring omega 0 this side, and I can go to write omega 0 plus alpha t. So you can see that this is omega 0 plus alpha t has the same form, which in case of linear velocity we had v is equal to v0 plus at, or more popularly you used to call it v is equal to v0 plus at. So this is our first kinematical equation. First kinematical equation for rotation. Okay, so I will not derive all, but then I will just establish the parallel. What was the second equation? So if you remember the second equation, it was v square is equal to v0 square plus 2a x minus x0 or y minus y0, depending upon what kind of motion it is. How do you get it here? So omega square is omega 0 square plus 2 alpha, and this is linear displacement. You replace it by angular displacement. Okay, so this becomes your second equation. This is second kinematical equation for rotation. Then I can go to the third kinematical equations, which is about the displacement. So in case of linear motion, you write x minus x0 is where x0 is the position at the time t is equal to 0, x is position at further time t, x minus x0 is the displacement, and that is equal to v0 t plus half a t square. Normally you are used to write in your school classes as s is equal to ut plus half a t square. At this level I prefer to write a more descriptive way of writing the equations. So you can see you can transform this. As I said, linear displacement is replaced by angular displacement. So I will write theta minus theta 0 is equal to omega 0 t plus half alpha t square, and this equation is going to give you as third kinematical equation. So the three kinematical equations are transformed into the new ones. Remember, as these kinematical equations are applied only when alpha is constant. Even these applies only when a linear acceleration is constant. If they are varying, then these equations are not applied. Then you have to go to the other form of writing the equations. Okay. So this way we can relate the two set of quantities. No, we have not. So let's put that to end today's class. So what is the relation between linear and angular quantities? What is the relation? So that we can figure it out. So you know that theta is s upon r. S is the linear displacement. So s is equal to r theta. That is the first relationship. Going to be very useful. You take a derivative of both sides. So ds by dt is r is a constant, radius. It will not change in a rigid body as we have described. So ds by dt is r d theta by dt. So this becomes linear velocity, and this is r omega. This is very important equation. V is equal to r omega. We are going to use it for a zillion time, but how are they related vectorially? Can anyone tell me, give the answer to this question on the screen? How V, R and omega related to each other vectorially in next 2 minutes? Because they are disjoint quantities. I can take derivative on both sides once again, and if I do that, then in that case I get an acceleration, linear acceleration, but this acceleration is along the tangent, along the line which is tangent to the circle on which the particle is moving. If you want more clarification over tangential acceleration and radial acceleration, you will have to go back and read the chapter on motion in two dimensions. It explains very clearly. If you have not understood the concept of tangential and radial acceleration, please go to that chapter and read it. It's very important also that you know it and you study it as well. Okay, so a tangent, this will give you a tangential and not a radial. A radial, which is required always, is because circular motion always require a radial. It is not this acceleration, it is tangential acceleration. So r alpha. So many a time this is written as a is equal to r alpha, but then you should not get confused. It is always a tangential is equal to r alpha. V is equal to omega cross r. That's right, Rishabh. You have a very perfect observation. V is equal to omega cross r. See, the cross product everyone should guess, because what happens is, as I have described, omega is in a different plane than V and R. So they are in perpendicular directions. In fact, all three are in perpendicular directions. So for a particle that rotates on a circle, you know that omega is moving this way. Of course, if the particle is going this way. Suppose if the particle position is here, then linear velocity is this way, and I would use another color, radius vector this way. So all three are perpendicular. Remember this. This is perpendicular to this, and these are also perpendicular. So omega cross r, if you curl your fingers from omega to r of the right hand, then your stretched thumb will go in this direction, which is in the direction of V. That's right. Remember, here I am taking the derivative of only magnitude. Here I am taking the derivative of only magnitude and I get this. Do remember that if you take the derivative of direction as well, you will get both. So I leave this as you people to explore. Explore this part. Take a derivative of dv by dt, vector v, and see what do you get. Because if you take the derivative of the vector v, then here when you took the derivative of the scalar v, r was a constant. Here if you take the derivative of vector v, r will not be a constant. So you have to apply u into v rule. And then you will get both the accelerations, linear as well as tangential. So I leave that, radial as well as tangential. So I leave that for you people to explore on your own. Very quickly, what we have learned today, we started with rotation of rigid bodies. We are trying to do kinematics, trying to understand how do the bodies move. So we defined what is a rigid body. We defined angular displacement. S is equal to r theta. Theta is s upon r. Their units and conversions. Then we defined angular velocity. Angular velocity is d theta by dt, and its directions and other units are standard unit radian per second, other units of revolution per second, revolution per minute. We saw how to convert them. We took a very simple example just to entertain ourselves with some numerical numbers. Angular acceleration alpha definition is straightforward, but alpha directions people get confused. If omega is increasing, omega and alpha in the same direction. If omega is decreasing, alpha omega in opposite direction. Omega constant, alpha and omega alpha 0. So check with your ceiling fan. I always tell students, it's there. You have a fantastic body, rigid body, which is performing a rotational motion at your home. Okay, when it is turned off, find out what is omega, what is alpha, what is everything. Suppose you turn it on, its speed is increasing, you figure it out, what is omega direction, what is alpha direction, etc. If it's moving at a constant speed, figure out what is omega, what is alpha, etc. And if it turn it off, speed is decreasing, you find out omega and alpha and displacement. In fact, if your fan can rotate at slower speed, like at lower settings, you can do a video analysis of the fan also and do a very fantastic project work from for rotational motion. So please try doing it if it's possible. Okay, so what happens if alpha is constant in time? Then we have three kinematical equations, just like three kinematical equation in linear motion, and the linear and rotational quantities are related. S is equal to r theta, v is equal to r omega. This is scalarly, vectorially, this is going to be my definition. Okay, and A tangential is R alpha. Okay, fine. So we can stop this